So my talk is about reverse engineering. I will also speak a little bit about Radar, which is a tool that I have been developing for about 10 years. So who am I? For those who doesn't know me, my name is Sergi Alvarez. I was born in Barcelona. Those are my Twitter handles. It's TrueFi and Radare2, which is the handle for my tool. And this is the website of the tool. I'm actually working in NowSecure, which is a company which focuses in mobile security. I mainly work on iOS, but I'm also doing stuff for Android and mainly doing research for vulnerabilities and looking for better ways for analyzing applications and detecting bugs and other kind of problems that may appear in mobile. So what's reversing? Reversing is the short word for reverse engineering. So, and the root concept of this is that reverse engineering means that you have to do reverse steps to the ones that you do for engineering. This is that you have a final product, and you want to understand how this final product is created. So you must do the inverse steps in order to grab all the information that you can achieve from this target. So for example, if you have just a file format, you can reverse engineer this file format in order to understand which internal structures are composed inside the binary. Or if you have a program, you can reverse engineer this program. You can do the same for network protocols. You can do the same for any kind of machine, even if it's hardware or software. So what's the purpose of reverse engineering? Many people think that reverse engineering is something evil or something that you are going to do for just stealing property information from other companies or things like that. And it's not really this. I mean, reverse engineering is something that you have to do in order to understand how something works. And it's something that it's really important for many things in our days. So for example, reverse engineering is important if you are going to find vulnerabilities, if you want to understand or find if a specific product is buggy or vulnerable. It's also important in order to bypass security protections and demonstrate that something is not as secure as the manufacturer is exposing. It's also important for extending functionalities. So there are different kind of things that you can do after reverse engineering. One of them is compatibility. I mean, so for example, there is people doing reverse engineering on Microsoft Office documents in order to create open source or a standard way for parsing these kind of files. The same happens for drivers. I mean, for example, network cards or graphic video drivers are mainly closed source, so people that want to use this kind of hardware in Linux, they have to reverse engineer the driver. It's mainly something that you have to do for understanding how everything works, and usually when you are doing this kind of things, you will find some hidden functionalities that are not exposed by the command line shell or the main interface of the software that you are checking. And well, where is Radar2 joining the game here? Radar2 is a tool that it's a free and open source tool that I wrote 10 years ago. I've been developing all this time. I never stopped it. I mean, if you check the GitHub, you will see that there are commits every day, like 20 commits every day and things like that. And there are many contributions. I have like 50 different contributors every release, and I'm releasing every 6 weeks. The focus on the main purpose of this project was to create a software that was free, that was command line based, mainly focusing and following the Unix principles of design. This means that everything should be considered a file, even if it's memory, if it's a hard disk, even if it's just a file or a socket connection, anything like that is considered as a file inside Radar2. As you have noticed, the 2 at the end means that this is the second version. In fact, this is a full rewrite of the Radar, which is it was a first implementation that I did mainly for fun. And as long as the project grew pretty fast, I had to rewrite it from scratch, almost everything. And actually, the current version is pretty stable, is really flexible, and you can extend it in many ways. And well, this year, as long as the project was celebrating the 10 years of the project, I decided to organize a congress, which was the R2Con, that happened in September. It was like many people coming here, more than 100, and it was like all the talks are in YouTube, so if you are curious, you can just check out. Okay, so what's exactly Radare2? Radare2 is a framework which is written in C. This means that it's really portable. It's also buggy in the sense that it's really easy to create bugs if you're writing in a low-level language, mainly because there are no ways to protect for doing silly things. And at the end, you have to spend a lot of time reviewing code. You have to spend a lot of time using different tools to analyze the binaries, the source code, all the steps that are in the middle before doing an end release. Like, for example, specifying that you have to do fuzzing before the release, and checking different file formats and checking all the tests, all the commits that are coming to the project must be tested. So there is like a huge test suite that we are running for each commit, and this takes like for about 20 minutes to run for each commit. So I'm trying to get better on this, and actually it's pretty rare that you have a segfault, and most of them are mainly null references, which are not really exploitable or hard to exploit. These APIs are automatically binded with Balabind, which is a tool that generates bindings for different languages, so you can use any other programming language in order to use the APIs of this tool. It's also extensible by plugins. There are many tools that comes with a framework. It's not just a set of libraries, it's also different tools that are using these libraries. And these different tools can be recognized because they start with an R and they end up with a 2. So if you can just identify them with an ls. And it's easy to extend it using scripts. It's really portable. I was focusing in portability, mainly because I used to work with many different hardware. I mean, I've been working with a Spark, I've been writing assembly for MIPS and ARM and many different hardware. I've been also doing stuff in PowerPC and so on. So I wanted my software to run in all this hardware. So every single device that I bought, I tried to port my tool to this. And well, another thing that was also annoying to me, it was if you're using binutils for disassembling code, you end up having to recompile or look for another toolchain in order to disassemble different binaries for different architectures, because there is no way to compile binutils for Intel, MIPS, and ARM at the same time. You have to build a different version for each architecture, which is pretty annoying if you are trying to, if you're, for example, in a CTF or competing in some kind of competition that you have to analyze different kind of binaries. You have to spend more time looking for different tool chains and so on. There are commercial tools that are able to do these kind of things, but I don't like to use anything that is not done by me. So I try to understand how everything works and do from scratch. So what can Radare2 do for me? Well, that's something that you should ask the other way around. What can do? What it can do is Radare2 can disassemble code, can analyze the headers of the binaries. It's able to support so many architectures and different operating systems. It's able to analyze code, data, references, and data structure. It's also possible to debug, trace, and it's used for exploiting. It's also used for binary manipulation if you want to inject code, any payload in a binary, or just fix any vulnerability. So, for example, I've been fixing vulnerabilities when I was competing in the DEF CON CTF in the binary. So I was grabbing the binaries from the server. I was analyzing, checking which kind of vulnerabilities that I was finding there, and then I was patching the binary in order to fix the bug. Also, it's able to mount file systems. I didn't explain that, but the thing is that this tool, I started developing it when I was working as a forensic analyst in a company in Barcelona. And as long as I was having some problems with a laptop that I was losing some files, I wanted to write a tool that was able to look for this kind of things in a hard drive. So I was just a tool that was an hexadecimal editor that was able to look for a pattern in a hard drive and give me the results, and then dump the results into the disk. So after this, I started enhancing the tool, implementing more functionalities like debugging, disassembling, and so on. And one of the main functionalities, or the original ones, was to use this tool as a forensic analyst tool. So it's supporting different file formats. It's also supporting different partition formats. And you can use it for mounting a file system and taking the files from there, for example. You can also use it for bin diffing. So if you have, for example, a system update or any update for any application, you can grab the old version, the new one, and check the differences. So you will be able to understand what the company or what the people that is releasing this software is fixing in this change, and maybe try to understand how to exploit it, etc. It's also useful for checking for computing checksums in blocks by blocks in different files. So this is pretty handy if you are doing forensics. It can be also used for analyzing, debugging, and patching kernel. I've been using it for patching OS X kernel, for example, and iOS. And it can be also useful for playing games or order pizzas online, and this is true. OK, so let's talk a little bit about plugins. Plugins are mainly binary blobs that are copied in a directory, and Radare2 will grab them and load them at the startup time. We can enumerate some of them. With the capital -L flag, it lists all the plugins that are loaded by this tool. As I said, there are different tools that come with Radar, not just Radare2. There is also Rabin2, which is the tool that extracts information from binaries. So this is all the file formats supported by it. It even supports Nintendo Game Boy and many other file formats. There is also Rasm2, which is an assembler and disassembler tool. These are all the supported architectures. Those are just some of them. There are many more in Extras, which is another repository, and you can install them later if you want. And well, that's more or less all the plugins that you can use. So for example, Radar2 is listing the plugins for connecting, which is the I/O plugins. The I/O plugins allows you to abstract the access to a physical device or remote target. So for example, it's useful for loading local files. It's also useful for connecting to the kernel. It can be also useful for mapping files and have the same views in two different instances of the binary. You can also load zip files, APKs, etc. So let's talk a little bit about the R2PM, which is the package manager that comes with Radar2. As long as the project grew a lot, I wrote a tool which is mainly simplifying the process of installing and processing the plugins that are needed for doing different tasks in Radar2. So if you need to install Keystone, which is an assembler from the Capstone guy, you can also install it by this, because it's not shipped by default in Radar2. You can also use the Red the compiler. There is also support for Unicorn. There are so many disassemblers from people that is contributing externally to the project. Also, all the bindings and different web user interfaces are available in this package manager. And you can check out the list with this command line, which is r2pm-s, which is searching for all the different packages that are shipped in the database. And you can see some of them here. OK, so let's introduce to the using of the shell. The main direction of the user that is using Radar2 is mainly using the shell. People usually get scared about the shell because it's a black screen with white letters and so on, and that's usually something not considered user-friendly. But everything in Unix, everything depends on the kind of friends or the people that you consider a friend. So I usually like to use the shell mainly because it's more expressive, it's more powerful. You can extend the functionalities of one tool with another one, and that's something that is not possible with graphical tools. So it's more easier and faster to develop tools in command line than doing it in graphical user interfaces, but it takes some time to understand how to use it. So as long as practicing is the best way for learning, I will start doing some demos and explaining some the main important comments. Those are the most important comments that you should learn for using Radare2. It's not that much. I mean, most people think that you have to understand everything in order to use Radare2, but that's not true. You just need to, for example, move from one offset to another one. So you use the S command, which stands for seek. If you want to get an X dump, which is an hexadecimal dump of a specific block of memory, you can use the X command, which is X dump. You can also disassemble code with PD. If you need to write something, you can use B command, which have subcommands for writing hexadecimal or assembly or anything like that. You can analyze code using the A command. And if you place a question mark at the end of any command, you will get the help of this. So every time that you are confused or you don't know how to do something, just type a question mark and you will get some more information. And finally, if you have to quit, just Control D or press Q. So it's not like ED. The experience is quite better than ED. So let's solve a simple crack.me using this tool, and we will see some different functionalities and capabilities of it. So the crack.me, I will not show the source code right now. I will show it later. But when you have to analyze a binary, the first thing that a reverse engineer is going to do is to get all the strings that are contained in the binary. Many people will use strings. The problem is that strings, at least the package that comes in most common distributions, is vulnerable, and it's possible that you can run and execute code because there are some overflows. So I prefer to use Radare2, which allows you to get the strings with -z, this flag. And -q means that it will show the output in a quiet mode. So it will not show the offsets and everything else. So you can compare the output like this. OK, so here we have the first string, which says enter password. The second one is hard level, something like that. And then there is U1 and sat end. So if we run the program, we can assume that the password is hard level, which is the strange string that is not related to the other ones. This is a pretty simple crack.me. It's not something difficult, but it's a way to exemplify the use of this tool. We can also open the binary with Radare2, and we will see that at the beginning we are placed in a specific offset. This offset is the entry point, and the entry point of the binary is the beginning of the program. So we can start disassembling the binary from here. And we see, for example, that there is an enter password here. I will explain more how to do these kind of things. So there is a enter password basic block, which is then calling to printf, then flush, then fget, then checking for eof. And there is a conditional that is if the file descriptor is finished, it will go to the sat end, and if not, it will go to the other basic block. Then there is a check for strlen and strncmp. And if this condition is true, it will jump to the U1. So what we are going to do here is we are going to patch this conditional in order to make the program always return true. So we have to patch this conditional, which is right after the strcmp, right here. So we need to change this branch, and we can do this pretty easily if we open the binary with the -BB flag, which allows you to write in the binary. By default, it's not supported to modify the binary at the end. So if we go to the strcmp, which is there, we have this jump if not equal. And if we use the plus and minus keys, we will increment and decrement the value of the byte. So we can change this jump just using the single key. So if we change this jump, we can run the tool and type any password, and it will say that I won. Okay, so let's see that we have seen that there are some information inside the binaries that we have to. It's interesting to grab it in order to understand what's the program doing or which kind of things that this binary can do. So the first thing is the entry point. We can grab all this information using grabbing2. If we use the -e flag, it will get the entry point, and the same for -q to only show the one value. We can list the symbols. If we list the symbols, we see that there is also the imports, which are inside the PLT, but there is also the other public symbols, which are exports in other file formats. We can also list the imports, which is all the functions that are called from other libraries. So for example, from libc or any other external library. We can also list the libraries that this binary requires. We can also list the relogs, and well, that's all the other information that we can extract. Grabbing2 also allows you to, I mean, it works with all very different file formats. I will show later some demos about this. But it's also useful for creating tiny binaries. So you can generate a tiny ELF binary or tiny PE binary from, so you just specify the bunch of bytes that you want to put inside the text section in the binary. And it will generate a tiny binary about 200 bytes, something like that. That works in Linux or Windows or OS X. Okay, so what can Radare2 do for forensics? As I said before, it's able to parse very different file systems and understand how different partition systems work. And I grabbed all this code from group. It's also able to detect the file magic. There is libmagic. I don't know if you use the file tool, which is pretty handy for detecting which kind of file format is contained. But if you do, for example, file/bin/ls, it will say that this binary is this kind of file format. You can also do the same with Radare2. So if you press PM, which means print magic, it will check with all the magic database in order to detect which kind of pattern matches with the header. You can do the same using /m if you want to search for magic. This means that it will check for every single byte inside the binary and match if something happens there. I mean, if there is a JPEG, I mean, this is useful if you are carving a memory dump or a hard drive and you want to extract all the known file formats from there. It's also able to parse different file formats and grab the data structures. It's also able to print data in different formats. You can, for example, print, if we are opening this binary, we can show in the disassemble using PD. We can show the xdump using px. We can also show using pc, which is print in C. If we need a Python buffer, we can just pcp. And as I said before, if you place a question mark at the end, you get the help. So you will see all the other code formats that are supported here. You can also see all the supported formats for the printing. So you can, for example, print the binaries in the binary output of the current block. It's also supporting in octal format and so on. So. And then there is also a hash, which is a tool that allows you to compute the checksums of different, for example, MD5, SHA-1, etc. And you can compute this of the whole file or by blocks. So this is useful if you are doing forensics, because if you have like huge mem dumps and you want to check which parts of this binary have changed, you can just compare the checksums of each megabyte block, for example. Okay, about graphing. Graphing is a pretty useful functionality that reverse engineers use for understanding what specific function or algorithm is doing. Radare2 supports different outputs for this by default, or the most accessible one is the str graph. I showed before this, but if you open the binary and you analyze the function using AF, you can enter in visual mode and then press B again, and you will see the graph in here. You can move the blocks and do whatever you like here. You can even debug and put comments, change the format of this graph, like showing the bytes or. What graphs are important is because they show the internal structure of the code. So you have, for example, a basic block means that it begins at some point, which usually is the beginning of a function, where other functions are calling to this entry point. And at the end, there is always a return, or a conditional jump, or a branch, or a trap instruction, or syscall, or any other kind of call that will not return at the end. So in this case, we have a conditional jump, and we are marking the flags, the two lines, with T and F. We can press the T or F keys in order to follow the lines. We can also use tab for switching from one basic block to another one. And well, at the end, you have a little understanding of what the function is doing and which kind of flows are happening inside. In order to understand and see better the information in a graph, you can change the format of it, you can add comments, you can also change the colors. You can also compute different things. So for example, if you press the uppercase R key, you will change the color scheme of the graph. You can also do the same in the xdump and same in disassembly. Another useful functionality of Radare2 is that it's able to compute the entropy, so you can get a graph of all the entropy of different blocks inside the binary. This is the entropy computation of different of the whole /bin /s. So we can see, for example, that at the beginning there is low entropy, which means that there is many repeated bytes in this block. This is because the header is here, and headers usually have a lot of repeated patterns, like, for example, zeros, which means that there is nothing in there, or there is an offset. At the end of the header, there is a padding, which is filled by zeros, so there is no entropy here. And from this point, there is the text section, which is where the code lives. And after this, there is the data, which have a lower entropy, this is because the code have higher entropy than the text have. By text, I mean strings and human-readable ASCII text. And there is some more binary at the end, which is randomizing from high to low entropy computes. And what we can see out of this is that, for example, if the entropy of the text section was really huge, I mean, reaching the end of the screen, it will mean that this block or the text of the code of the binary is encrypted or is compressed. So if you check this with an UPX binary, you will see that the entropy is much higher than it's normally in a normal binary. Also, something that many people miss when using Radare2, and they come from either or Hopper or other graphical tools, is they miss the navigation bar. There is also a navigation bar in Radare2. You can enable it by setting up this command. And you will see it at the top of the screen. If we analyze all the binary, you will see that the uppercase F means that there is a function in this position at the beginning. There is the beginning of a function. We can seek around, so there is an arrow that points the place that we are located. And it's showing where there is text, where is data, etc. Okay, so let's start talking about debugging. Debugging is the action of spawning a process, attaching to it, and stepping into the instructions and being able to dump the memory from the process. Those are the main basic operations when you are debugging. And Radare2 is a low-level debugger. This means that it doesn't really focuses or prioritizes the support for having source code. So if you have the source code for an application and you want to debug it, it's usually better to use LLDB or use GTB or any other debugger that is more focused on source code. So what's the point of debugging in Radare2? Radare2 is a low-level debugger, which can be considered something like OLEDBG from those people that comes from Windows. It relies on code analysis. It relies on binary information, so you can grab all the symbols and strings and all the references from different functions, and you should be able to understand what the program is doing or what's happening when you're debugging. So the main, I don't know if you know a little bit about how really a computer works internally. I guess that you should. When you are debugging, you basically have a stack, which is a piece of memory that is growing or shrinking depending on how many of the recursivity calls inside the binary. So when you are calling a function, the stack is smaller. And when you are returning from this function, you are getting these bytes back again. So you have the stack, you also have the resistors, and then you have the code and all the memory from other libraries. We can list all the memory using the M command. This is all the mapped regions inside the binary. So when the system loads this binary, it will allocate different regions in order to put all the pieces that are required to run, like, for example, the heap, which is the dynamic allocated memory, all the libraries that are depending on it, all the stack, and other information, other maps that are useful for working. Okay, so the stack is needed for storing information of the backtrace. So if you want to see where you're coming from a specific point, you have to analyze the stack. So for example, we can use the pxr command at rsp, which is the stack. And this command will try to analyze the stack in order to extract all the words that are found in there. So it will grab, in this case, I'm in a 64-bit machine. And we can see that it's grabbing every 8 bytes. And this is, for example, a pointer to this section. Then there is a pointer to the string of the binary. Then there are 2 zeros, and then there are some more pointers. If we analyze which strings are these, we will see that this is the different environments that are exposed inside the binary. So we can see all the environment variables, all the XB, etc. Okay, so coming back to the debugging shell, we can press S to step into, and if we want to step over, we have to press uppercase S. So let's go into a jump, into a call. So here is a call. If I press lowercase s, it will go into. And here is another call, so I will just change the program counter. So I'm in the instruction before the call, so I will press uppercase S, and this will step over the call. So it will run the function, but it will not go into this place. This is useful because if we are analyzing a binary, we don't want to go into analyzing the libraries that are, or the functions that this program is calling. So we don't want printf, for example, because we are interested in the program. So we have to step over this kind of calls. As I said before, there is a PXR which analyzes the stack or the memory that you are pointing, and you have also seen that I'm using this @sign. This @sign is used for setting a temporal seek. So you can use, for example, sRSP for seeking there, or you can just x at RSP, which is a temporal seek to this address. So, okay, so there is PXR for analyzing data, and there is DRR for analyzing the registers. So registers here is the fastest memory available for the CPU. So it's important that, for example, if we run modern CPUs used to have more registers than all ones, and they try to be in the same size of the architecture. So, for example, if we are working on a 64-bit binary, we will have to use the 64-bit registers, but it's also possible to use a 32-bit or 16-bit, etc. So here, for example, we see that there is different values for each register, and we can see that there is RX, which have a nasty character, which is a printable char. There is RDX, this register, which is pointing to this, which is in fact a pointer to an address that is pointing to another address which contains this string. So then there is RBP, which points to the base pointer of the stack, and RSP, which points to the stack. So we can see, for example, that the space that is between RSP and RBP is the contents of the stack frame. This is the local functions, the local variables of the function are stored in this place. So we can use, for example, px at RSP, but we want to see that we have to subtract the two offsets in order to check the size of this. So in the function that I'm running right now, which is actually inside DLD, which is the binary loader of OS X, this function have allocated in the stack this chunk of bytes. There are other commands. Everything for the debugger is under the D command. And we can, for example, send signals. We can change the behavior when a process receives a specific signal. We can change the file descriptors. We can, for example, close the standard in file descriptor or change the standard output file descriptor to point to a new allocated file descriptor that is maybe a socket or maybe a new file. We can change everything at runtime. It's also possible to check the backtrace using dbt. dbt is a command that implements different algorithms in order to extract the information of the stack. This is useful because, for example, if you are using GDB for debugging and you are having a crash and you want to understand why it's crashing there, if the stack is really messed, you will not be able to understand where this function is coming in. So DBP allows you to specify where the RSP is, so you can easily specify the newly allocated RSP if you have, for example, able to recover the old value of the stack. You can also be able to specify that you want to use a specific algorithm or another one. You can also specify that just want to show all the keywords that are in the stack pointing to an executable section, so you will see all the pointers to code, etc. If you want to step, just use the ds command, which this command allows you to do other things, like, for example, stepping until a specific address, so dsu, and then, for example, we can continue execution until the entry point. So we are now in the entry point of the binary. We can also use assisted debugging, which is mixing emulation and debugging. And this kind of functionality is handy because sometimes you want to understand what an instruction is doing before executing it, and being able to place some kind of conditions like, I want to stop when this register is pointing to this address, or when there is any register pointing to a specific address or range of memory, etc. There is also possible to set up breakpoints using the db command. The DB command allows you to write software and hardware breakpoints, and there is also support for memory breakpoints. And as I said before, it's assisted breakpoints too, which is mainly focusing on emulation. But this is just the native debugger of Radare2. Radare2 have so many plugins. This is just one of them, and we can use also other debuggers as backends for Radare2. One of them is Frida, for example, which is a dynamic tracer that allows you to inject a JavaScript virtual machine inside any process, and then you can talk to it by sending scripts and run code inside the binary. It's also supporting LLDB, GDB, Box, WinDBG, and other debugging servers. So you can use Radare2 as front-end for them. So for example, what's the benefit of using Radare2 instead of using LLDB? Or you will ask these kind of things. Because Radare2 is having other functionalities that other tools don't have. So for example, if you want to analyze or get a graph of the functions or get all the references for a specific string and so on, this is not possible with GDB, at least. You need to install some kind of plugins or some scripts that you have to run after it, etc. Radare2 have all these kind of things inside. It's also possible to do code patching. It's easier to modify code. It's easier to modify memory or change or understand what the specific function is doing. And well, what's the backend of LLDB useful for? Well, LLDB is the de facto debugger for Apple ecosystem. So if you are debugging iOS, iWatch, Apple TV, or OS X applications or binaries, you have to use LLDB mainly because it's the debugger that is supporting more functionalities, and it's pretty well maintained. In fact, GDB has been crashed a lot in the past, and I'm happy that at the end Apple is releasing as open source all the work that they are doing in LLDB, LLVM. Well, so you can, for example, one of the problems of LLDB is that the disassembler is really a mess. I mean, it's not really good. There are many instructions that are not supported, mainly if you are working in ARM and ARM64. So if you are trying to disassemble or trying to understand why a crash is happening in an iOS application, you will have to copy the bytes that you are having from a specific range and then copy it to another tool and disassemble from this tool. Mainly because if you disassemble from LDB, you will see a lot of invalid instructions, and that's not really handy for understanding what's going on. And well, there is also support for Box, which is a low-level x86 emulation, emulator for PCs. There is also support for GDB servers, so you can talk to a remote GDB session, and same for WinDBG. So there is also possible to attach to a Windows that is running and talk to the kernel, and then you can modify the memory or do whatever you want to do there. So let's do a Frida demo. In order to install Frida, I had to install this plugin, R2 Frida, so I just type this command. And after this, we can see the plugin in here. And the description of the plugin says that we have to use the Frida peekaboo. And we can do, for example, this, like launching Twitter. And we will attach to Frida. OK, so we are inside Frida right now. How can we get information from here? Using this command, or this prefix, allows you to send a command to the target debugger. So if we press the question mark, we get the help for the commands that R2 Frida is shipping for us. And we can get information from the target binary. We can list, for example, the symbols of lib system, for example. Wait. So those are all the symbols that are exported by libc. And we can check, for example, which is the address of strcmp. So we can go there. and disassemble the memory from the strcmp inside the process. All this communication is happening by communicating different JavaScript scripts that are talking to the C plugin that is running inside Radar. So we can patch this instruction, for example. We can change strcmp to do something else, but we will do something more interesting. We will see all the classes, Objective-C classes that are loaded inside this application. We can do this using the IC command. And we are interested in the classes that have something related to Twitter. And we will list all the methods of the class, which is called Twitter API. So after checking some of them, we will see that if we are looking for something in the search part of Twitter, we will see that there is a callback that is executed every time that the results are coming back to the application. And this one is called did get search results. So if we do this, we'll see that this method is in this address. This is the code of the callback that is executed when the results of the search are happening. And what we are going to do here is just return. We will set the return value to 0, and we will return. We can do this by first changing the protections of the memory. So we have to use the dmp command. We have to say the size of the page, and then the protections. We will set everything with read, write, and execution permissions. And now we are able to inject code here. So we are do a short rax, and then read. Short rax is basically setting rax to 0, which is the register that is used for returning values to the caller. And if we disassemble, we see that this is the code that is actually here. So if we check what's going on now in Twitter, is that nothing is happening. We can patch back by changing these bytes. So we have seen that we have patched 4 bytes. So we have to copy the 4 bytes from the original function. So it's basically this. And if we try to search again, the application is working. For patching, we can also use the visual assembler that allows you to patch the code at runtime. We can do things like that, for example. And Radare2 is also able to track different patch sets, so you can have different patches and then enable and disable them at different points of the debugging. So you can set breakpoints in different places, and when the execution is happening there, it will set some breakpoints or patch some functions, etc. Okay. Let's make another quick demo for debugging. So what we are going to do here is to solve the crack.me. This is a different crack.me, and we will solve it by debugging. Okay. Yeah, I patched some instructions. Okay, so we are now debugging the crack.me, and we want to go to the entry point. So we are here right now, and we can see, I will drop the bytes to get some more space. So we can see, for example, that in the main function of the program is getting some references to some interesting strings like enter password, printf, flush, fget, fail, strlen, check password. So we see that there is something happening in the check password. We will go there, and well, I went there by pressing the number that is at the right So just pressing the number 7, it will jump to this. If we press U, it will go back. So it's like a stack of different offsets. So we analyze the function, and we go to the graph. And if we see the graph of this function, you will see that there is a loop. So there is a jump that is coming back to another basic block. So it's running this loop between 2 basic blocks until a specific condition happens, and then it's going out. And after this loop, it's calling strcmp. So what we can understand here is that so there is some kind of process, and this process generates a string that is compared later with the input of the user. So we are going to run until this address using the DCU command and then the address. Yep. Wait. There is a little bug that I found yesterday here. We have to do here is just step overs until the fget happens. So if we step over here, we see that there is a call to printf. Then there is the call to flush. Then there is a call to, so we see the output of the enterer's password. Then it's asking for the password, so we input stuff. And we continue doing step overs here. So what we want to do here is to go into the check password. So, oh, damn, I pressed step over. Okay, so I will press lowercase s and go into the check password here. What we can see here is that there is this is the stack. We can see that there is password, which is the text that we have entered in the input field, and we can also see that if we are stepping in, it will basically jumping around the loop. So it's repeating this process. And one of the things that we can do here is just look at the stack. If we increment the size of it and we continue stepping, we will see that there are some bytes that are changing here. And now we will see that the condition is not matching, and it's going outside the loop. And we see that there is this string, which is passed to the strcmp. At this point, we can use the array in order to grab the values of the registers and where they're pointing to. And basically, we're interested in these two registers, the RSE and RDI, which is the source and destination registers, and they are used as the two main arguments for calling a function. So we see that it's checking and comparing the password that we have typed in the input, and the pass, which is the password that is checking by we can do, for example, here is just changing the value of the register and continue the execution. But as long as we have debugged the binary and we know the string that is compared, we can just try this password, and it works. One of the things that are pretty handy in Radare2 is that as long as everything can be scripted, there is also a tool that allows you to set up an environment for executing. So there is Radare2, which is a tool that defines this kind of environments. If we run it, we will see the default profile or some sample. And the execution profile allows you to say, for example, which program do you want to run, which arguments you want to specify to it. You can change the environment, you can change the CH root, you can change the user ID, you can the group ID. You can tell, for example, that you want to connect to another host and change the standard in and standard output file descriptors to the sockets of this connection. You can listen for it, you can fork, you can do so many things. You can also preload Radare2 inside a process. So when the process is receiving a signal, you get a shell of Radare2 inside the process. And we can automate this execution using Radare2. So this is the prompt, the script that you have to write, which is basically saying that program is the crackme, and the input is the pass with a new line at the end. And we can run this like this. So this is handy because if we have to do some kind of fuzzing or we want to automate some processes, we can do all these kind of things inside Radare2. These profiles are also used by Radare2. So if you are debugging, you can load this profile inside Radare2, and then it will set up all the environment for debugging. So you can start debugging in a separate CH root with a different user ID than the process is expecting at the beginning. I don't know if you know what's Dirtico. It's a vulnerability that was explained, or well, it was exposed some weeks ago. And it was affecting all Linux machines from 8 years ago or something like that since now. And there is, well, there is a bunch of exploits around there. I basically took one of them and wrote an EO plugin for Radare2. So well, this is, I need the virtual machine here. Okay. Can you read the text here? Okay, so the Dirtico package is shipped with R2PM, and you can just install it like this, Dirtico, and you will grab the code. The Dirtico vulnerability allows you to write in any file that is owned, well, which is not owned by you, but maybe by root or any other process. It basically means that it's patching the copy on write protections of the kernel. So when you are reading a file, you are not reading the file itself. You're reading from a cache. And this cache can be triggered with this exploit, which is a race condition between two different operations. And we can, for example, change the etc services or etc host, anything like that. We can check the permissions if you don't trust this thing. So I'm not able to write in this file. I can do anything here. I can write because I don't have permissions. But if we use the code, we can read it. We can seek at another offset, and we can write something here like hello world. As we can see, that nothing changed here. The reason for this is because this is a race condition, and the race condition usually depends on the number of iterations that you are doing the same thing. So this will work in some cases, or some machines, or some slow machines, like maybe mobile phones or routers or things like that. But if you need to do the same operation more times, you can just prefix the command with a number, and this will run the command 100 times. And we press X, and we see that the file has been patched. We can confirm this by using cat or head, maybe. So as you can see, you can use the I/O plugins of Radare2 in order, as a way to exploit or get some benefits from different exploits. And this is pretty handy for analyzing the vulnerabilities or dumping memory kernel, stuff like that. OK, so I think I'm running out of time, but I will try to go a little bit faster. About analysis, there is okay. OK, so as I said before, there is support for analyzing different kind of file formats and architectures. We can see, for example, that it's supporting ARM64 binary. We can type AA in order to analyze all the code that is there. We can type more A's if we want to do more analysis in there. The reason for this is because there is no single way for analyzing everything. So you have to do some kind of understanding before typing the comments that you are going to do. So depending on the architecture, depending on the kind of binary, depending if it's encrypted or not, you will have to run different comments. So just by running this, you will analyze only the symbols. As long as this is a stripped binary, it will not do anything, because there is only one function considered at the beginning of the entry point. And if you want to grab more information, you can also change the configuration in here and for example, set up this variable and run AAA, which is doing more work in there. This is trying to find all the functions that are inside the binary, and it will, at the end, or if you press Ctrl+C, you will list all the functions that it have found. You can also see the size of each function and sort by them by cyclomatic complexity, etc. Like this. Analysis is useful because it saves some time in order to identify some references, in order to see where this function or where a specific function have been called from, etc. I will go for a seal. A seal is an intermediate language that I invented some years ago. The reason for creating a new intermediate language is because there is none that solves this problem. The problem that I was trying to face here is that I was trying to find a single representation for expressing what a specific instruction is doing. And about what a specific instruction is doing, I mean any instruction from any architecture or anything. So what you have to do here is, many people try to solve this problem by defining complex structures and trying to use unions and trying to specify very complex representations for this. But at the end, you have to do a very specific representation for each architecture. And at the end, as I said before, debugging is basically a stack, registers, and memory. So I tried to abstract this in a seal, which is basically a string that represents what each instruction is doing. So if we go there and type uppercase O, you will see that it's changing this assembly to some strings. And these strings are representing what the instruction is doing in the roots. So a push is basically decrementing the stack and saving a value inside the stack. If you know Forth, or it's a very simple stack machine, virtual machine, it's pretty similar to this. So it's easy to understand when you understand how this kind of stack-based virtual machines work. And the good thing of this is that it works pretty well. So we will try to solve the same problem, the same crack me that I did before, but using a seal. When you are loading binary, if you type -d, it will debug. But if you don't place any command line flag, you will just get the static analysis view. But if you press P again, you will see that there is a stack, some kind of debugging view of the binary. And there are registers, stack, etc. But there is no stack. There is nothing like that. So you can type AAM, initialize the stack and the registers. So we are not able to press S. And we are emulating the code from inside Radar without having to debug or run anything like that. This is useful for people which is analyzing malware, because they are usually want to understand what the specific function is doing without having to run the malware in there. Otherwise, it will be pretty harmful. So what we are going to do here is basically change the entry point. I change the register of the program counter, which is RIP in this architecture, and point to the check password function. So we are now stepping into this function, and we will see that we are doing exactly the same. We will go to increase the stack, and we will see that the string is getting created in the stack, just in the same way that it was created in the debugger session. Okay, so let's go for the last demos. As I said before, one of the most important things in Radare2 is that it's pretty easy to extend it by using scripts or writing any kind of automation process. And this can be done in any programming language. I mean, I wrote Radare2 which is a very simple interface for talking with Radare2, which basically consists in one command. The command that you want to use is cmd, which runs a command in the target Radare2, and the return value of this command is the string that represents the output of the command. So you are just calling commands and getting the output, parsing it, and running other commands. We can see, for example, that there is this crackme, which is basically the source code of the crackme that you saw before. And we can solve this using R2pipe in Python. Here we are opening the crackme. This is statically opening, and we are not debugging at all. We are seeking to a specific symbol. Then we are initializing the seal virtual stack and so on. Then we are changing the program counter, and then stepping until the call to strcmp. And at this point, we can just check the values of the error, and it will grab the password from memory. So if we run this script, it will just show the final password that you need to type. So as you saw, I don't know if you noticed, but this script is pretty silly. I mean, it's just sequential. There is no single loop or parsing anything of the output. So we can just rewrite the same in a script for Radare2. So it's just one command per line, and we can run the same using the -i flag in Radare2. And this is the same, but using Radare2. If we want to experiment a little bit with the R2pipe, we can use Python, we can use Node.js, we can use any other supported language. We can check this here. Those are all the supported languages. There is Dlang, there is Swift, there is C#, there is Java, there is Rust, there is Bala, etc. So there is a lot of commands and a lot of programming languages that support this API. And the reason for this is there is no single way for talking to a specific Radare2 instance. One of the most common is just spawning a Radare2 instance and then talking to it by using standard in and standard output. But it's also possible to use the same API and use HTTP, talking to a remote HTTP web server of Radare2. You can do the same using pipes. You can use the same using the native calls of the function, just DL opening the library, etc. So this is binding for Radare2, which is simpler than using the API, because you are just interacting using commands. And there is one functionality which is pretty handy in Radare2, is that if you place at the end of the command a J character, it will output in JSON format. So if we do like this, we press I to get the information from the header, and we change the last character with J, we will get the JSON representation of this. What's good for this is that R2pipe have a command that abstracts this. So you can R2pipe open, and then R2cmd, and then you can get the output like this. or you can see the JSON. But if you want to get the JSON, you can just call the cmdj command, which is parsing the JSON and returning a native object for the language. So after this, you can access all the JSON from here, like this, for example. OK, so to finish my talk, I will talk a little bit about the user interfaces, because that's one of the main concerns of many people that start using Radar2, because they are pretty scared about the command line and so on. So there are so many different user interfaces. The main one is the command line one. You can, if you open the binary, you can press uppercase V for going into visual mode. Then you can press the admiration mark to go into the DWM-like interface, which is a tiled view of different panels. You can create new panels from here. You have some menus. You can check, for example, analyze the function or analyze the full program. You can see all the calls, check the references to this call. You can search for strings, tools that are maybe assembling some code, checking a calculator, etc. There are also games here. You can just play. And apart from this, there is also the web interface, which is maybe the easier way for writing user interfaces. So if you type this command, it will launch the internal web server from inside Radar2, and it will launch the web user interface. This is the material web user interface, which is similar to how Android looks like. And you can see the disassembly like this. You can check the information of the binary. You can see the graph in str here. You can also debug. Enumerate all the comments. You can also filter them. You have a console, so you don't miss the capability of running comments in there. You can see all the flags, etc. The web user interface is probably not as native as Qt or anything like that, but it's pretty handy and it's pretty easy, very useful. And this is by the default user interface in the Android application. There are also other web user interfaces that are native. So I wrote a bunch of them. I wrote Radar, which is a graphical interface using GTK. I also wrote Ragi, which is a non-released user interface in GTK and so on, but it's really boring, so I don't really focus a lot in doing these kind of things. And now there is a new user interface written in C#, and maybe we'll get to something soon. They are focusing he's focusing on Windows, but it will be probably go into supporting Linux and OS X. And that's all. Questions? M'he passat de temps, no? Sí.
So do you have a documentation on the tool on your
Sure.
website?
There is, if you go into the webpage, there is a bunch of talks and there is some links to YouTube and so on if you want to see some talks from other people. There are some tutorials and people solving crack maze with it. There is a book. I wrote a book for Radar1, and there is a bunch of people that have been updating all the comments for Radar2. Okay. And if you go to IRC or you use Telegram, there is a channel in there, and there is like 500 people in there. So if you have any question, just ask there.
Cool. Thank you.
Cool. Any other question?
I'm still recovering from the fantastic tool. Have you found any case of countermeasures against Radar in
Yes. In fact, it was like 1 month ago, something like that. There was a malware for routers that was checking if the Radare2 process was running in the same machine. And it was like, I mean, it's the classical protection for GDB or OLEDBG or either that it's happening in malware or in Windows. But it was the first time that there was this kind of check for Radare2, and I was like quite proud of it because this means that it matters for something. Yep.
And you've taken measures, anything extra measures?
Well, you can patch the binary. I mean, you can or just rename the binary of Radare2. Yeah. There are always different ways for solving this kind of countermeasures for analyzing or debugging. Yeah. Okay. So.
Okay. So thank you. He was Sergio Alvarez. Thank you very much.
So this is the first time that I come to this Congress, and I'm pretty happy to collaborate and give a speech here. It looks like there's a lot of interesting talks, and it's relatively close to my home, and I would like to repeat next year. So thanks for the opportunity.